Hey everybody. So this is a super interesting research paper that caught my eye for multiple reasons. It's called Comprehension Without Competence: Architectural Limits of LLMs in Symbolic Computation and Reasoning, put out by Amazon Web Services, or AWS. And then just like a kind of a note, like a simple highlight with these research papers, sometimes they'll be like, you have an author and they'll be like AWS or Microsoft or whatever, but they could be like generally like a professor or like someone that's like unrelated, or they could be doing research that's like outside of the organization. And then it would typically say here, like, so it says here, like submitted to the research institution that it's submitted to, but then it could say like researched outside of AWS, or like, along those lines is like kind of how they'll word it generally. So, but within this particular research paper, like this is clearly like this was funded by AWS, like on AWS time, etc. Like, and to me, that's like important within this because this is like I'm assuming Amazon's stance within this, right? And then overall, like I 100% endorse this research paper. Like this research paper backs up every single thing that I have found and researched within these models. And so let's dive into it overall. Like the big claim overall within this research paper, putting it into simplistic terms, is that LLM models have a syndrome. We'll call it computational split brain syndrome. And then so what is computational split brain syndrome? It's very unique, and it's opposite of the way that humans learn, which is why it's hard to dissect and kind of like wrap your head around overall, right? But so the bottom line is that the models create two different vector pathways depending on what they are trying to do. So the models inherently are pattern predictors and next token predictors, and they have a feed forward mechanism. Those two things are very important within this research paper because this research paper states that those are the two fundamental bottlenecks, the two issues within AI overall that create this problem, which are like the two most lasting parts of AI overall, right? But so within that, these two factors and elements combine to create a situation where the model essentially let's take arithmetic, for example, like 5 plus 5, and the model sees like a bunch of problems associated with this. It starts to understand that 5 plus 5 equals 10, right? And it understands the pattern of 5 plus 5 equals 10. And I've dove in like quite extensively into that concept of that on my channel, right? That it's not actually like 5 plus 5 what it learns. It learns the pattern of 5 plus 5 equals 10. And then so every single time that it sees that, that's what it predicts, right? And then so that's how it works. But then executing 5 plus 5 equals 10 is a completely different concept than knowing it, right? Like knowing that 5 plus 5 equals 10 is different than what is 5 plus 5 equals 10. And then so when that 5 plus 5 equals 10 comes into play, the model utilizes a completely separate vector track. So it's like two completely different universes for the model, right? 5 plus 5 equals 10 is one universe. What is 5 plus 5 equals 10 is like a completely separate and different universe to the model. And then within that, there are other inherent problems that come into it, that which this paper does a fantastic job of diving into those problems as well, right? So the problem when you get into executing 5 plus 5 equals 10 from the model's perspective is that it runs into all forms of mathematical complications within there. Going back to this split brain problem, let's analyze that further, right? So our equation is 5 plus 5 equals 10. And then in this instance, no matter how you are imagining it, we're utilizing the numerical representation. 5 plus 5 equals 10, right? But the numerical representation, the number 5 in your mind, right? The closest text correlation to the numerical representation of the number 5 would be, I'm assuming, 5, F-I-V-E, right? That makes most intuitive human sense overall. The closest textual representation to the number 5 that they found within the models that they examined within this was 15, F-I-F-T-E-N. And then so the models have a problem breaking down and classifying the mathematics and the pure components of the latent space within that is what that breaks down into, right? And then they found that like there's some numbers where they just have no like correlation whatsoever, like the numerical concept, like say like the number 7 has like no. This is actually like it starts at like they say very specifically like 11 and 12, right? There are the two ones that they cite specifically. So like 11, like the number 11 has no correlation whatsoever to any number. like it's not correlated in the model's latent space to a number at all. And then so when it goes to do that execution, that's the vector that it's operating off of, right? And then so you can ask it all day long, like, what's the vector, like what is 11, right? And it can give you textual understanding and complete like the pattern recognition side of what is 11. But when it comes down to that execution, it's operating again on like a separate highway, and that highway doesn't have, it literally has nothing connected to the number 11. Overall, it's kind of like that's what's going on within this. And then so this paper very specifically what they do is so they outline that problem, right? That there's the models utilize this they call it contextual averaging, and then so limitation of this and why this occurs within the models. They highlight this somewhere within the paper very specifically. They dive into it very nicely, where they mention overall that hyperbolics like that, like I look at it as there's a problem that develops within this, right, between hyperbolic space and Euclidean space, where they directly mention and they notate that like a problem within this and like why the model has those problems with directing which vectors it should go and how to place those vectors like specifically within its latent space properly are due to problems overall within hyperbolic space. And then they're very smart to note and to not notate that they're not directing or dictating that the solution to that would be to operate within pure Euclidean space, because that wouldn't be the solution to that, right? But that does create a very unique problem within this, where this problem at its most structural level, even if we're stripping away, like going beyond like the feed forward mechanism and the pattern recognition as the two main problems, we strip it even further than that and a layer deeper than that. There's a mathematical problem that is like at the core of this, right? Which is that essentially, if we utilize hyperbolic space for these models, it will amplify pattern prediction and everything associated mathematically with pattern prediction, but we can't utilize hyperbolic space, especially for the latent space, in order to get extremely precise calculations of the latent space and utilize that geometry like we would want to, because of the inherent limitations and what happens within hyperbolic space compared to Euclidean space overall. But because of those differentiations, that's exactly why we want to utilize hyperbolic space in other instances for those benefits. So that creates this unique problem, right? And I'll dive deeper into that because I have a kind of a temporary solution for that overall. And then so this paper, the next step that they do, so they outline this problem and then they break it down mathematically, right? They provide three claims and 3 algorithms. Claim 1, contextual averaging prevents automatic domain binding. And then claim 2, feed-forward networks resort to pattern storage. So it's like feed-forward networks are an inherent problem within this. Claim 3, next token prediction decouples instruction from execution. To me, like this research is so, if you understand like the history of AI overall, right? Like you have the introduction of the perceptron in 1956, and then you have by Rosenblatt, and then you have the Minsky paper that comes out in 61, which like completely just obliterates the Rosenblatt paper, right? And then that's what causes the initial AI winter, et cetera, et cetera. And then architecture gets changed from there. Jeffrey Hinton takes it forward. We're here where we are today with AI. To me, if attention is all you need is the Rosenblatt paper in 56, this is the Minsky paper in 61. Like that's the best way that I can equate this. Like, and like, again, like I 100% endorse this research paper. Like I see no flaws with this research paper. And then what it outlines from there. So from the math, they go into everything, like all of the problems that and the ways that people go about trying to solve for this. So like self-scaffolding, reasoning models, etc. Right? And then the problem with these models is that like the core fundamental problem within the architecture that this creates is a disconnect where it is literally impossible for the model to know what it doesn't know. Like that's where the disconnect, this split brain problem comes in. And then this split brain, and it's because of the architecture of the model itself, right? Because of the fact that it's a predictor and its job is to predict the next token, coupled with the fact that when it very first starts this information, it's in a feed forward process, and how that feed forward process kind of just bundles that information initially, creates these initial parameters for this to happen, and it becomes unescapable within this mathematically. It's like just the full breakdown of how this operates, right? And there's no, like, you can't escape it. And I like, makes 1,000,000% sense to me, and this backs up and it jives with all of my research within this, right? And then again, it's very counter. This overall is counter to how humans learn. It's like the exact opposite of how humans learn, which makes it like a hard overall to understand and to deal with LLM models overall, right? Because it's a different problem that they face than humans typically. So typically, in order to have mastery, you first have to understand, right? Like you have to know. So it's knowing leads to mastery is like how it works, right? Like if I want to learn how to play basketball better, I can study basketball and practice, and then that's what's going to lead to mastery, right? Within the and repetitive examples of it over and over again of shooting the basket. But within the LM model, that knowing doesn't translate or transfer into actual understanding. They're two different avenues. So if you're training up and the repetitive shooting, it will become like the greatest shooter of all time from that specific spot where you're training it from, right? And it will be able to do that all day long, but that's not going to transfer any, like it's two different pipelines. Like the highways are not connected is the problem within that. Like from that to generalizing that out, which is like the generalization problem within these models, right? And so this is very specifically highlighting that current architectures will not be able to solve that generalization problem very specifically because of these problems, right? And then here in section 5, they have the compensatory strategies and their execution gap. So self-scaffolding, which is leveraging comprehension for step-by-step execution. Tool delegation, which is like bypassing the model entirely. And then hybrid architectures where you have specialized models for symbolic operations, which this does work well, right? Like, so if you have like a very, like, again, but it's because of that generalization problem. In this instance, you're not asking the model to generalize anything. So actually, like, it's only executing one function. So it can pattern recognize to figure out how to execute that one function. And then lastly, then you have, they dive into essentially the mathematics behind this. And then so they introduce 3 algorithms behind the 3 different claims that they make. And then so to me, this paper is like super well constructed overall, right? I'm a fan of this paper. I like it and what it's doing. But so let's dive more into from the theoretical into the practical within this, right? And there's a few things that I want to highlight and point out within this. And then so I've been very much like endorsing this paper, right? And then so I'll give you a few experiments and examples as to like why 1,000,000% I endorse this. So recently there's been like a lot of hoopla about this researcher, he pitted different LLM models against Atari 2600 in chess, right? My initial assumption within that was that he set up the experiment wrong. Like when I first read these, I was like, that was my first assumption, was like, okay, like these garbage articles, like blah blah blah, right? But then I did some experimentation on it, and I haven't made a video on it because experimentation didn't go out. It didn't go and happen the way that I expected it to happen, right? So I've been waiting for it to be able to showcase this, but so here it is, which is like Gemini plays chess, right? And then so very specifically, I'm utilizing Gemini in this instance, Gemini 2.0 Flash, and then I'm giving it. So my assumption was that like he was just like prompting the model, right? So it's like Atari 2600, here's the move. Like here's what they did, and then the model has to like represent and keep track of like the entire like board within its latent space and all that. So it's like, okay, like that would be a very hard challenge for anyone overall, right? So I figured like I'm gonna give it like essentially the regex of the individual moves. I'm gonna give it like the full ASCII vision of the board, of the current board state. I'm going to give it a prompt filled with all of the legal moves that it can currently make for that particular position. Like give it literally like all of the scaffolding around it that it needs, right? So essentially, like it's given this every single time, and then you can see here Gemini is thinking, and Gemini chose a move, right? And then it checks whether or not it's a valid move or not. The opponent in this instance is a simulated Atari 2600. What that means is that the opponent is just flat out making random moves, Atari in this instance chose a good random move, but this is like you can tell this is a random move, right? This is not the optimal move. I don't know. I'm not a chess master overall, but that does not seem to me to be the most optimal move in this instance. And then I don't know, this is an odd formation overall, but again, it's just guessing and randomly doing this, right? This game, to save you some suspense, if I scroll all the way down, it goes. I stopped it at like 400 and something of so I can't even scroll down all the way to it, but it's like 400 and something moves in. Gemini, and it's Gemini 2.0 Pro, right? It's printing out here Gemini 1.5. I changed it to Gemini 2. Like I wanted to give it like every advantage possible that I could within this. Gemini stalemates against a model that is literally just making random moves. Over 400 and something moves of this game. You can have access to this notebook, do whatever you want with it, change the model out. Here's the scaffolding for it. Having an LM model play chess against a random move maker, and the LM model's not going to win. Spoiler alert. That goes very specifically into this, right? Other example of this would be like the Claude-based Pokemon. There's a reason why you haven't heard about that for a long time, right? It's because Claude after 6 months now hasn't even beaten half a Pokemon, and the reasoning is exactly as this research paper lays out, that there's a fundamental disconnect, and it's due to the architecture between the model knowing and the model executing. And then the other thing to break down within this very specifically with regards towards the math before we dive into the code here is that the model very much breaks this down into geometric terms. Another concept that I've been talking to you about for a few years now on this channel, right? Which is essentially that the fundamental, from the model's perspective, what breaks down within this is the geometry breaks down. The geometry between knowing and the geometry between executing are two different geometries, two different shapes of geometry. And then again, going back to that hyperbolic versus Euclidean space, there's instances where you want hyperbolic versus Euclidean space within that, right? And then so that creates a whole bunch of challenges within this. And then so as this paper lays out, and I 1,000,000% agree with it, this is a very deep-seated architectural problem, and the architectural problems where it's seated are at the two oldest parts of AI overall, just plain and simple, pointing that out. And then so like, I do very much look at this paper as like a Minsky 61 type paper within this argument. And then so I agree with the analysis that short-term solutions wouldn't be the way forward. But if I had to engineer a short-term solution to this, utilizing existing model architectures, this is what I've come up with, right? Which is Metacognitive Geometric Scaffolding, or MGS. And then so this is a simulation of that. So this notebook provides a Python-based simulation of metacognitive geometric scaffolding, a theoretical AI architecture designed to overcome the reasoning failures commonly observed in standard LLMs. The core concepts. Inspired by the research paper that we're talking about here, this prototype simulates an agent that can reason about its own reasoning. And that's the fundamental problem that all of this breaks down to, right? I explained all of the math behind it, but what the core fundamental problem that means and what it lies and how it breaks down to is that the model has no way to actually execute and perform a calculation of what it knows versus what it doesn't know. And then so it directly addresses, so this framework directly addresses the phenomenon known as computational split brain syndrome, where a model appears to understand a task, but consistently fails to execute it correctly. The key mechanism behind this is metacognitive self-assessment. So this is done in 3 steps. 1, you have a hybrid geometric space, as I talked about before. So the agent represents a given problem in 2 distinct ways, and it creates 2 vectors within this. Like, so every single time it faces a problem, it creates 2 vectors, an instructional vector and an executional vector. An instructional vector is a deep logical structure mapped in simulated hyperbolic space. An executional vector is a familiar, solvable pattern encoded in Euclidean space. So the executional vector operates exactly as the model is used to as a pattern prediction, right? 2 is introspective divergence. The agent calculates the geometric divergence between the instructional and the executional vectors. This provides essentially that scaffolding that it needs in order to, here's a framework that you can use to know if you don't know. And then so a high divergence score indicates a gap between logical understanding and practical capability. 3, strategic action based on divergence. The agent uses the divergence score to select a reasoning strategy, execute for simple low divergence problems, scaffold for complex logical problems that require decomposition, delegate for tasks, for example, like complex math, best handled by external tools, and then confess uncertainty for nonsensical or unsolvable inputs. And then so the outcome, this simulation showcases how the MGS agent dynamically adapts to different problem types using metacognitive reasoning. It highlights a more robust and self-aware form of AI, bridging the gap between comprehension and competence. Like, overall, so essentially what you're doing up front with the model is you're giving the model a toolbox, and then you're saying, okay, here's the prompt. Here are 4 different toolboxes. Your first job is which toolbox is the best for this, and then if it's whichever the toolbox that you pick is, that's the one that will execute off of, right? And we'll go off of. And then so for this first problem, we say, what is 2 plus 2? And then it decides that it can handle this itself, right? So it chooses its own universe. It chooses to execute. And then so it says 4. And then we say, okay, cool. Now, problem number 2. Alice has 4 sisters and 1 brother. How many sisters does Alice's brother have? And then so in this instance, it chooses to scaffold. And then it does that because, so essentially it performs this calculation, and then what ends up happening is it realizes that it needs to utilize the instructional vector, or that hyperbolic space, very heavily within this problem compared to utilizing its like Euclidean or like very formalized mathematical space, right? So then it decides to scaffold. Then when it scaffolds, it breaks the problem down step by step. So it reasons it out like a reasoning model, right? But the problem, again, going back to reasoning models, and this has been a highlighted problem, is that the model doesn't know what it doesn't know, and it can't reason when it doesn't know. And then so this essentially solves for that, right? It's like, do I know enough to reason? Yes, it's scaffold. And then in this instance, calculate 742 times 89. 742 times 89 is much harder than 2 plus 2. And then so it says, I don't know, I'm just going to delegate to the math tool, right? Cool. That's exactly what you want. Then it's going to just have a calculator perform it, and then a calculator will perform it, and then boom, there's the answer. And so the model's not doing this calculation. It's delegating to the calculator. Cool. And then so last problem, if a fish can climb a tree, how long does it take to make the sky? And then it comes up and then it realizes like very heavily that this is in the hyperbolic space, but almost nothing within the Euclidean space. So it has nothing, no lower ground to ground it to, which is this is nonsensical, right? So then of course that's what's going to happen. And then so it chooses confess uncertainty. After analyzing the problem, I have determined that it cannot be solved, that it's semantically nonsensical. The premises are logically invalid, providing an answer is not possible. So it gives it the actual option to choose uncertainty, right? Which is a problem within these models, right? They're this split brain problem. And I see this, people get mad at these models for this, right? They call it the model's lying, about this. And it's no, dude, the model has a brain disorder overall, where it can't understand what it doesn't know. And the model has the Dunning-Kruger effect built in times a million. That's the most simplistic way that I can break down what exactly is going on here and what exactly this paper is highlighting. And then so overall, long term, this paper is it's flat out stating that our current architectures are not the way forward, which is it's interesting in the stance of Amazon, right? Amazon overall has not been very big with regards towards generative AI. They've been huge with regards towards robotics. If you look at Amazon's investments, they're all in on robotics, almost nothing on LLMs. And generative AI overall. They have, Amazon Poly, it's an afterthought, right? They have, all of their generative AI is afterthought. We have to have something in this market, so let's put it in. But you can see their eggs are not in this basket, and they haven't been. And then so you can see it very specifically and very clearly within this, and they highlight why. I guess to me, I look at it as there is so much money invested in this architecture overall that it is either going to work enough for what people need it to work for, or the entire economy is going to collapse. That's my approach to these things overall. And then so again, I 1,000,000 bajillion% agree with this research paper. All of my research backs this up. Gemini loses to random moves. It can't not even an Atari 2600. It loses to a baby. I don't know how else to frame that and highlight that overall. And this is a critical problem, and as they highlight and point out, it's a critical problem of the framework, and that critical problem of framework doesn't go away. But it doesn't mean that there's no use or application for the models overall. Just highlighting that it's you're going to be hitting your head against the wall if you are looking at this problem in any sort of conventional way whatsoever. I'll leave a link to all of this for you, so you have a link to both the research paper and then as well as both these collab notebooks. And if you like this type of content, please like and subscribe. Thank you much.